All right, let's get this thing working. This has been a weird day, isn't it always? So, I don't blame everyone for being out. It is too beautiful a day. But I can't teach electric circuits outside, or I would. So that's what we're going to do. And where I'm going to start off is a couple of, a little bit back, a couple of lectures back, where we're talking about the electric field inside of conductors. This is where the slides need to go forward. So, all right, we put some charge in a conductor and we allow it to move. All the charge feels a force on it from each other. They're all repelling and they're all in something that's easy to move, so they all move. Eventually, they come to rest at the surface and at the interior of the conductor, there's no electric field. And that's true throughout the conductor, right? The electric field starts at the surface because that's where the charge is, and it doesn't go inside, it goes outwards. So with the electric field 0, then we can calculate how the potential changes through the surface, which is that it doesn't. The change in potential is 0, which means for any given conductor, the potential is a constant. We don't know what number it is. Right? And that's kind of true for everything else we've done with potential. We care about the difference, not the actual number. But it's some constant value, and it's generally determined by the conditions in our problem or in our setup, whatever it is that we're doing. Right? So when we start talking about circuits, we're going to have a lot of conductors. And the point of it is that all the conductors that are connected together have the same potential. Now, there's going to be things that are not conductors, and that's where the potential can change. So how do we put a particular potential on a conductor? One way to do it is to use a battery. You've done this in the lab. Batteries have a chemical reaction inside that effectively pushes electrons to one terminal and removes them from the other. So you'll see a few different terms used for potential difference, and you'll see them in different contexts as well. For a battery, and when we get there to start talking about magnetic fields, you'll see what's called the electromotive force. It's the ability of the thing to push charges around. And then colloquially, we call all EMF and all potential difference, we call voltage. That's what the electricians would use. All right, and it is common enough that I will say voltage when I mean potential difference. So, I mean, you've seen different sorts of these. The lab, you saw the little cylindrical cells, the D cells, positive terminal on top, negative terminal on the bottom. And they have symbols for them. All right. And the symbol has a longer line is positive and the shorter line is negative. You've also seen car batteries. I assume at some point car batteries have a positive terminal and a negative terminal. And the voltages for batteries are dependent by the chemical reaction going on inside. So it depends on the makeup of the battery. But in general, you can pretend that they're constant, at least until the battery dies, until the charge runs out. So if we connect wires to a battery, all right, here we have a car battery, it's 12 volts, and we connect wires to it. Then we can make some statements about the conductors in here. That's not the slide I want. All right. So this wire here, this is at 12 volts. This wire here, everything that's connected together, we can say is at 0 volts. Now we're defining this. We could very easily put 0 at the top and minus 12 at the bottom. The point is that the potential difference between the conductors has to be 12 volts. So we could set it however we'd like. We could set it to be 1,012,000 on top and 1,000,000 on the bottom. So when we make an electric circuit, you might think, well, let's just connect these wires together. What would happen? Well, we have a problem because once we connect them together, they're at the same potential. But we've defined them to be at different potentials, right? Because the terminals of the battery are different. And what happens is a lot of current flows and it gets real hot and breaks. Or is that you basically mess things up a bit. So what we do is we put something there that is not a conductor that will use the energy involved in the current flowing. Right, so we'll have something there, and the potential difference across this has to be 12 volts. Because we can find a wire connected to it that's at 12 volts and a wire connected to it that's at 0. So for a realistic example, car battery, 12 volts, and we hook it up to a light in the car. And that light is not a conductor, it's a resistor. It will use energy, it'll turn energy from electrical potential to light. And as current flows through it, you'll see a potential drop across the light bulb. And that's what you should have saw in the last couple of labs. When you measured potential differences across light bulbs, you saw that there was something, right? That you basically measured, when you made a measurement across a circuit, you basically compared one wire to another, and you saw that one wire was 12 volts higher than the other wire in potential difference. So we defined voltage earlier and we did potential. Voltage for circuits is just going to be the difference in potential between two parts of the circuit. Current is going to be the flow of electrons. It's a change in charge past a point over time. Normally when we say delta Q, we mean we're taking charge away from a point. And here what we're doing is we're looking at a point and seeing how much goes by, the rate at which charge flows. And we define some units here. Charge is in coulombs and time is in seconds, and those are amperes, or amps is colloquial. So we also have I here is our current. For reasons, I is used, historically they expressed it more as an intensity. All right, so you might expect it to be C for current, but that doesn't make sense. We have already used C, and so it's just one of those weird things, and we just go with it. Like Q is charge. Why would we use Q? So we can define different types of current based on the long-term behavior of the charges. All right. If we push charges through a circuit and it's always pushing in the same direction, then we call that direct current. The charges actually travel over time. If what we do instead is just wiggle the charges back and forth over a small distance, so they don't really move, and they just oscillate around their position, sometimes going one way, sometimes the other way. That's what we call alternating current. Now, if we wanted to, we could go in, and your textbook actually does this. It goes in and talks about what the electrons are actually doing. Right? We've talked about this a little bit with sound, is we can look at the speed of the individual particles in a gas independently of the speed of sound in the gas, right? As the particles bump into each other, the information carried by the sound wave travels faster than the individual particles. That's not perfectly true, but you have a big distribution of speeds for sound, and then you have one speed for, no, not distribution of speeds for the particles, and then a separate speed of sound, which is some high number that most particles are going slower than. That's what happens for electricity, is that the electrons are generally moving just a few centimeters per second. But the shove, the battery pushing an electron into the wire and taking one out of another wire, that current is fast. That's much faster than the actual shove. Most of these particles don't move very far. It takes a long time for an individual electron to go around the circuit. But the information, the energy travels a lot faster. So we have a problem to work on. We're going to hook up a calculator to a battery. Battery is 3 volts. And the current used is 0.17 times 10 to the minus 3 amps. Now, we're getting into where, you've seen this with capacitors, you've seen it with electric charge, using the SI prefixes. All right, so you just have to remember the milli is 10 to the minus 3 and keep that in mind. So we're going to let the calculator work for an hour. We're going to ask how much charge flows, how much energy does the battery deliver? And so we can calculate, all right, we know that the current is rate of charge over time. And we know that the energy way back from potential is charge times potential difference. So I'm going to let y'all calculate for a second, and then I'll show the answers. So if we're going to find the charge, it's going to be the current times the time. If we're going to find the energy, it is going to be the current times the potential times the time, just replacing in Q. And of course, I think in the slides, we go and take carefully. All right, we calculate the total charge, and then we just use the total charge. And so what we get is, over an hour, the energy used will be about a couple of joules for, a 3-volt battery and a 0.17 milliamps. This is not too bad. That makes kind of some sense. You don't expect a pocket calculator to use a lot of energy like an explosion or a car engine or something. It uses not that much. So that makes sense. Okay, so I'm going to go back for a minute. These equations that I've written out here, we're still going to end up using them in different ways. So But generally for circuits, there are better equations to use. I do want to talk about one other thing is generally when we talk about current, we talk about what's called conventional current, which is we mentally model that positive charges flow from the positive terminal of a battery to the negative. They flow from high potential to low potential. Now, we asked you a couple of times in the lab, can you tell which direction the current is flowing? And in general, you can't at this point. You hook up a circuit, the light bulb glows, you don't know if it flows through it from left to right or right to left, let's say. And for a while, we didn't know this. This idea of conventional current is we have to pick a direction so that we can talk about what's going on in the circuit. And we don't know which way, so we got a 50-50 shot. And we picked wrong because we thought positive charges would be moving. But then we identified that the nucleus of atoms were the positive charges. And this comes from our definitions of positive and negative for static charges, for static on an object. We determined that the positive charges were not moving and the electrons, the negative charges, were. So the actual flow of particles through the circuit is electrons flowing from negative to positive, from low potential to high potential. For everything we're going to do, that does not matter. But in real electronics, once you get into, say, the calculators and the phones and the computers, everything that has transistors in it, everything that has electrical switches, you have to consider that once we have electricity flowing through semiconductors, through the chips in your computers and such, you have to consider that the electrons are actually doing the moving. If you try to do conventional current, it doesn't work as cleanly. So we can figure out what's moving, and 100 years ago or so, we did figure out the electrons were the things moving. So just be aware that the way we talk about things in one context is not what's actually going on. But in this context, it doesn't matter. We're always going to do conventional current going from positive to negative. So we talked about resistance in the lab. Resistance is defined as the ratio of voltage to current. The idea is that you plot. So you control the amount of current that flows through an object, and then you measure the potential difference across that has to be across it. And what you get is some nice function with a slope R. And that's our resistance. And we generally write it as R is V over I. So an object is in the circuit. It resists the flow of current and allows there to be a potential difference between the wires connected to it. Current flows through, and we can predict the potential difference in the current from the resistance. Now, the actual definition comes from, well, we have an object that resists current. How do we know how, what is the material properties that deal with it? But more importantly, we're going to define this Ohm's law, which is the relationship between potential difference, current, and resistance. This is the equation for circuits. This and what I'll define next when we talk about energy. We have some units. Units for resistance is the ratio of volts over amps, which is ohms. Ohm's law, and the unit ohm is named after a guy, Georg Ohm, who did a lot of studying about resistance. And I'll show some findings here in the next couple of slides that are kind of extra, but note that these are, you know, a volt is 1 joule per coulomb, and 1 amp is 1 coulomb per second. So the ohm in terms of SI units is really messed up. It's like joules per second coulomb squared or something. No, joules second per coulomb squared, right? We just stick with volts per amp. That makes sense. And in every context we're going to use it, that's what we're going to use. All right, so any sort of thing that resists the flow of current is a resistor. That includes wires. You may have seen this in the lab as you started hooking up 3 or more bulbs in parallel. The ones furthest from the battery were just a little bit dimmer than the ones close to the battery because the wires had a little resistance. And so not as much current flowed through the far wires as through the near wires. Example problem, we have a flashlight. Flashlights, this is getting, you know, these still exist, obviously, but 1, everyone uses their phone if they need a flashlight. And 2, a lot of people now have like purpose-built flashlights that are rechargeable or whatnot. This is the old style. You put 2 batteries in it with a bulb. And that is to find the resistance of the bulb. If we use 2 1.5 volt batteries and it delivers 0.4 amps. Well, this is easy enough, right? We have Ohm's law. So the resistance is voltage over current. And then we just multiply things out. So we have 1.5 volts times 2, or 3 volts, divided by 0.4 amps. And then we'll get something in ohms. And when we calculate that out, it's 7.5 ohms. And if you measured light bulb resistors, if you measured the resistance, that's what you would get. You'll do measuring of resistance in the next lab. And it'll just be take a meter and probe it. We'll have meters available at some point. All right, here's where we get into the material properties. How do we know the properties of a resistor? And we're not talking anything, you know, how it's, you know, you'll see in the lab next week, you know, little tiny component resistors. You'll see, you know, we've seen light bulbs, they're different. We're going to talk throughout these slides about things like the resistance of extension cords and house wiring, things like that. The resistors take all sorts of constructions, but they're effectively a pipe. And electrons flow through the pipe. And if you make the pipe skinnier, all right, if you make the cross-sectional area smaller, then the resistance goes up. Or if you make the pipe longer, the resistance goes up. All right, so we have the cross-sectional area and the length are important. Unlike pipes, it also matters what type of material it is. Is it a conductor like copper, which is very easy for electrons to flow, or is it a material like glass? It's very hard for electrons to flow. So this rho here, which again, we're reusing symbols, this should be density, is also resistivity, and it has units. The units have to work out. L over A will give you units of 1 over meters. So to get resistance in ohms, resistivity has to be ohm meters. And that seems to trip students up, that multiplying 2 units together. This is where it trips people up the most for whatever reason. various materials. And what we note for the resistivity is the conductors are all very low. We're looking at 10 to the minus 8 ohm meters. Semiconductors, the stuff that, you know, is in your phones and computers and calculators and such, are all going to be on the order of like 10 to the minus 5 to 10 to the 5, around 1, but a fairly big range. And then insulators are all going to be very big, 10 to the 11, 10 to the 16 ohm meters, which kind of just tells you what you already know. Conductors have very low resistance, and insulators have very high resistance. Right? If we built two resistors out of the same shape, I'm just use one of glass or one of Teflon and one of gold, obviously the gold one will conduct more electricity. Where does that kind of matter to you? It matters when you start like plugging stuff into the wall. Right? Is it lots of stuff you buy has warnings? Don't change the cord on the thing. Don't use extension cords with it. All right. As here's an example. You want to run a lawnmower that's electric, and you want to know the resistance of the extension cords you could use. Wires are, when you specify the gauge of a wire, you're specifying the cross-sectional area, but what you're doing is you're doing it weird. You're basically saying how many wires can be made from a certain amount of material. So 20 gauge wire means you make 20 wires from a unit of material, which means that it's thinner, it's smaller than a 16 gauge. But we give you the gauge sizes exactly, right? So we give you cross-sectional areas, you know, 5 or 13 times 10 to the minus 7 square meters. All right, so if we want to know the resistance of a wire, and I'll write through A here. All right, so A is 35 meters of 20 gauge wire. Then our resistance looks like this. Generally, this is going to be one equation plug and chug. All right, so this is going to look like, and then we write out terms, 1.72 times 10 to the minus 8 ohm meters times 35 meters over 5.2 times 10 to the minus 7 meters squared. Meters all cancel out, you get ohms. You get a number that's not very big. It's going to be on the order of a couple of ohms. And when we calculate that, all right, for part A, you get like 1.2 ohms. Makes sense. So for the longer wire, you would expect the longer wire to have more resistance. And to make up for it, you make the wire fatter. You make it have a larger cross-sectional area. And that's why you do that. So where it matters to y'all is if something tells you to use a certain wire or not to use extension cords, you should do that because that keeps you from burning your house or your apartment down. And sometimes you want to use a particular cord on an appliance as a safety thing to keep the appliance from destroying itself. Like one time I rewired a light bulb, like a lamp, and the cord I put in was too big and it blew the light bulb up. Like let it shot out of the thing. But a thinner wire would have limited the current going through the bulb, saved the bulb. So, you know, you want to be careful of that sort of stuff. Replace wires with the same gauge if that's, you know, if it's working. If it's not working, and you basically let someone that knows what they're doing do it. So this is extra. This is Not anything you need to know, but generally what's going on, this is the relationship between thermal conductors and electrical conductors, is the particles that are moving in the conductor are generally the electrons. So thermal conductor can conduct heat easily because the particles are moving around. And it's also an electrical conductor since it's charged particles moving. So the resistance of a material can depend on the temperature. Basically, a higher temperature means particles are moving faster, and generally that means that it's a lower resistance. Sometimes, sometimes it's a lower resistance, sometimes it's a higher resistance. I shouldn't say generally. But things that follow Ohm's law, generally when you heat them up, they have a higher resistance. They're called ohmic resistors. And there are also non-ohmic resistors, which do weird stuff. They you heat them up and the resistance goes down. And then there are some objects that generally have a stable resistance with respect to temperature. So this is completely extra, but you may notice this in places. Is that if you've ever looked at the power used by an object, they have these things so you can inspect and see what's using power and basically what things are costing you money. You turn on something like a light, the instant you turn it on, it uses a lot of power because it's a high resistance. And then it warms up and it uses less power because it's a lower resistance, or vice versa, depending on how the thing works. Anyway. All right. So we talked about voltage and current and resistance. And the point of all of that is that we make a circuit to do something useful. We put an item like a light bulb in a circuit, or a heater, or a computer, a calculator, whatever it is. We put an object in the circuit to make use of the energy, to transfer the energy from one form to the other and do useful work. So we want to figure out how much energy is available in the electric current. And the way to do that is to look at energy over time, right? What we're doing is that the power is energy over time, and then the energy is Q delta V over time, as we defined from the previous chapter. Right? The electrical potential energy is the charge times the potential difference. So when we do that, we realize, oh, we have the change in charge. Right? The idea is that we're carrying energy by pushing charges along. So each electron carries a little bit of energy with it and gives it up when it goes through the resistor to do useful work. So we're counting the number of electrons that we're delivering, and each electron has a little chunk of energy. So what we're doing is measuring the current and multiplying by the potential difference. And so we have that the power is voltage times current. And this is going to be, these two equations are the fundamental ones. You should absolutely remember those equations. Those are the ones we're going to use throughout. Everything else is how to apply it. Those are the two that we're going to use. Because we're dealing with things that are resistors, we can write this in other forms, but this is always true. Power is voltage times current. That is always true. The other forms we can take is by replacing one of the terms with its equivalent from Ohm's law. All right, so here we're replacing voltage. And then here we're replacing current. And so we get alternate forms. In general, this equation is generally used with things like energy loss. How much energy is dissipated by a resistor when a certain current flows through it? And that's important because, you know, if you build a circuit and you want it to be efficient, you have to care about where the energy goes. But in general, if you have resistors, all of these, why did you do that? That's not what I wanted. I just wanted to erase this extra note. So in general, all of these equations are useful in some, you know, you can, basically you have four things you can know. All right. And you can use any combination of two of them to get the other two in principle, right? Is that you have relationships between these four variables. All right, so an example, we want to know the power delivered to a light bulb in a flashlight. We use 3 volts and 0.4 amps. So remember that when we did this circuit before, the resistance of the bulb was 7.5 ohms. So we could use that if we, you know, we could find that if we wanted to. But in general, this is nice and neat. We have the current I and the potential V. So the power is voltage times current is 3 volts, 0.4 amps. That is 1.2. And in our units, we'll have joules per coulomb times coulombs per second, which is 1.2 watts. You see that the units of power come out of this when you do it correctly. And then the total energy is just the power times the time. So if we use it for 7 minutes, I think it was 5.5, sorry. 5.5 minutes is 330 seconds. So the total energy will be something like 400 joules. Now, you could also do power is V squared over R. And, you know, we use the R we had before. And so this would be 3 volts squared over 7.5 ohms. And you get the same answer. 9 divided by 7.5 is about 1.2. And you could do P is I squared R, and you would get about the same answer. Now, if you did that, P is I squared R is 0.4 amps squared times 7.5 ohms. And it's also 1.2 watts. So I'm going to pause there. Does anyone have any questions thus far? All right, so I'm going to do a little bit of this, and then we're going to call it a day. At least I'm going to do the series stuff, because you've seen that in the lab, and that's straightforward. And Thursday, we'll go and start doing the parallel stuff. And then next week, we'll do complex circuits. So you connect a bunch of stuff in a circuit, right? You know, like the lights you put in the circuit in the lab, or Christmas lights. Lots of Christmas lights. Strings are in series. You know, one of them goes out, they all go out, or in a branch of the circuit. All right. So What we're caring about is circuits where the current flows through every device in the circuit. There's one loop. Now you can draw your finger along, and there's one loop, and all the resistors are on that loop. So what happens is the current that's delivered by the battery goes through each thing. And what you found is that each resistor has a different voltage, right? If we do this with the numbers in the lab, say the voltage here is 4 volts, and these resistors are the same, then these are 2 volts each. So all the current flows through, the voltage divides over the resistors. All right, so if we look at that, well, we can replace the voltage by the total current times each resistor. And that's what we do. We have our expression, the battery voltage is voltage 1 plus voltage 2, and then we just replace those. So current times resistor 1 and current times resistor 2. And we can factor out the common current, but we can also look at it as the circuit is a lump with a series resistance. And the current that flows is based on the potential of the battery and the circuit. And so we can express it as a series resistance. And what we get to is that the resistance of a circuit made out of series parts is just the addition of all the resistors. And that's kind of what you saw in the lab, right? In the lab where you're comparing brightness and such. You added a light bulb, you doubled the resistance, and so you have the current, you have the brightness. And if you added a third bulb, you would have tripled the resistance, and so you cut the current by a third. The gist of it is that the battery, the potential difference in the battery can provide a maximum amount of current, but it doesn't provide the same amount. That's what you saw in the lab. It provides essentially enough current so that the total potential difference across the resistors equals the potential difference of the battery. So we can identify the potential across all of the components. You know, say this is a 4-volt battery that we used in the lab, right? Then this wire here should be at V is 4 volts. If this wire here is at V is 0. So this wire here should be at V is 2 volts. If R1 is R2. All right, this is from the lab. At equal resistances. So we can identify one conductor is at 4 volts, another conductor in here is at 2 volts, and then the third conductor is at 0. So the point of this is that as we're doing circuits, this Ohm's law and the power law, we can apply not just to the entire circuit, but to any portion of the circuit, is that they have to be true. Generally, you just have a thing and current flows through it, and there's a potential difference across it. And the Ohm's law has to apply for resistors that have that current and potential difference across them. So we can go through and look at some examples. All right, we want to find, in this problem, we have 2 resistors. They're hooked up to a 12-volt battery. They're 6 and 3. So think a bright light bulb and a dim light bulb. So we want to find the total current, and then we want to find the power that's used up, the power dissipated So we're taking the electrical energy, we're turning it into heat and light. We want to find the power used in that process, and then the power delivered by the battery, which should, because we're conserving energy, it should be just adding up the power. So we look at this, and what we realize, these things are in series, so we just add them together. All right, so 6 ohms and 3 ohms is 9 ohms. And then we find the current, I is V over R, is 12 volts over 9 ohms. 12 over 9 is 1.33 amps. Then what we're going to do is say, well, that current flows through each resistor. So we'll start with the 6 ohm resistor. And I'll switch color here for a second. And we want to know delta V for the 6 ohms. We apply Ohm's law. This has to be I through that resistor times R, which is 1.33 amps times 6 ohms. And that has to be 8 volts. Now, for the other one, which I'll put in blue here, there's 2 ways to go about it. We can do the same math. We can do delta V for the 3 ohms is 3 ohms times 1.33 amps, which is 4 volts. Or we can realize that the potential across each resistor has to add up to the battery. And so that has to be 12 minus 8, which is 4 volts. So we can inspect it, or we can calculate it, and it works both ways. So this has to be 4 volts. Now, what we can do is, in a bunch of different ways, we can calculate the power, right? We could do power is voltage times current. And if we did that, we would do the power in the 6 ohm resistor is 1.33 amps times 8 volts. But we could also, right, and what's easier is to use the numbers you're given in the problem as much as possible. We can calculate the power is I squared R. And so we're going to multiply that out instead. And I'm going to show you what that looks like. All right, so first we find the series resistance, that's 9 ohms, that's what we expect. And then we find the total current is 1.33 amps. And then we go through element by element, resistor by resistor, and we figure out what the power is used there. And the reason you can calculate the voltage there is this also has to equal 1.33 amps times 8 volts. Right, because these things also have to equal voltage times current. And then the total delivered by the battery is the addition of those things. Okay, so I'm going to pause there. Do y'all have any questions thus far? This makes sense in some ways. Some people have to think I don't know what the chat is, what the Zoom call is doing, but all right. All right. All right, so I will introduce parallel resistance and then we'll go home. You've seen stuff in parallel, right? You've hooked up bulbs in parallel in the lab, and what you saw was that the brightness did not change. Effectively, it looks like a couple of circuits overlapping. you can pretend that there is one circuit. You draw one loop. And then independently, there is a second loop. And the stuff in one branch of the circuit, in one loop of the circuit, doesn't affect stuff in the other loop unless they share the, if you took the battery out, both bulbs would go off. But stuff in one branch doesn't affect stuff in the other branch. And so what we find in parallel wiring, things share a common voltage. All right. Let me erase this drawing here. All of this is one conductor with one potential. Say this is delta V is 12 volts. Then all those wires are 12 volts. And then all of these wires would be at 0 volts. Which means that the potential across each resistor is the same. Right? So when we do our thinking about stuff, what we note is that the potential does not divide across branches. It divides across individual resistors. The current does not divide across individual resistors. It divides across branches. All right. So the analogy that we often use with students is water flowing through pipes and pumps. Let's say you have a you have a faucet, you turn the faucet on, and then water is being delivered by a pump to that faucet. If you fill up a gallon jug out of the faucet, the water has to have a gallon flow through the faucet, and the same gallon has to flow through the pump at some point. But you could also have two faucets in the house and fill it up half a gallon out of one faucet and half a gallon out of the other. And there's different rates, big faucet, little faucet, you have different rates of flow. They would be delivered, that water would be delivered by a pump somewhere. So, it's just pushing that flow of water, and the water divides. So you can think of the flow of electric current like a flow of water. If it branches, it's going to divide up. It's not going to divide up when it goes through different chunks of the pipe, different resistors. How much it has to be pushed, how much energy gets used up is based on the potential difference. And that follows loops. It doesn't follow branches. Water analogies do eventually break down, but they work at the beginning. And we want to talk about parallel wiring because the stuff you use in modern life, everything you plug into the wall, is effectively one great big parallel circuit. Somewhere, power plant delivers a bunch of electricity and it divides up in parallel to a bunch of power lines. Power lines divide up into more power lines, like it's like a tree. You have a trunk, branches, and limbs. And each house is like a leaf. And you get a bunch of holes in the wall that deliver the electricity, a bunch of plugs. And each plug is effectively a parallel branch. So you plug in a TV and you plug in your stereo. Do people use stereos anymore? I figure everyone uses their phone. You plug in your TV and you plug in your lights and you plug in your phone charger and a hair dryer or whatnot. And it would be horrible if you plugged all of those in series, and when you cut the TV off, you couldn't dry your hair. Or when you cut the light bulb off, the TV also went off and you're sitting in the dark. So everything has to be in parallel. That's the only way that it would make sense to do it. So Yeah. I'm going to come back to that one. So when we talk about parallel wiring, we'll eventually have some weird rules about adding resistors up, which at the moment, I'm just going to say that if you have multiple branches, then it has to be easier for the current to flow. You have to have a lower resistance. And this math allows you to have that lower resistance. You can't add up the resistors normally because you would get a higher resistance. So you have to find a way to add them up. It gives you a lower resistance. And this matches the physics, is that we know the current splits and we know the current has to be potential divided by resistance, but it's the same potential because it's the same conductors. So we end up with the thing in parentheses has to equal some thing in parentheses that represents the resistance of the circuit. And so you get this rule for adding up stuff in parallel. That's where I want to stop for the day because that's enough. For forecasting the week, what's going to happen is tomorrow will be a lot of practice of adding stuff in parallel and combinations of one battery and multiple resistors. Stuff where that we can do it without any extra information. You know a lot of stuff now as it is. Monday, you'll do a lab, and the lab will be dealing with the resistors, showing that resistors in series and parallel work, how to work with resistors in a circuit, like if you were trying to prototype something, how to work with electrical components, and then resistors and capacitors, which will come at the end of this. So I really probably should do that, but I'll do it on Thursday. That's more of a natural place to put that, I think. Tuesday, we'll deal with multiple sources of potential difference, multiple batteries. How do you deal with weird circuits you could have, which are not unreasonable? One of them you could have is like in your car. You have a battery, and then you have an alternator, which charges the battery from the motor. And then you have a bunch of resistors, so you know, your lights, your sound system, whatever, things that need to use the electricity. How do you deal with the fact that there's two voltage sources? And then lots of practice, right? So it's going to be lots of practice problems and getting comfortable with reasoning about circuits outside of actually having them in front of you. And that should take up the next week. So, y'all have any questions? No? Go home. Enjoy the day. It's awful pretty out there.